Now, circular motion, let's go ahead and look at an example problem. So we have a ball of mass m going around in a circle. The length of the string here to the middle is going to be L, and it says find the min speed to complete the circle. Now this is a vertical circle, not a horizontal circle. So the first question you have to ask yourself is, if I'm going a min speed, where's the last point of failure? Where can I mess up and not complete the circle? Where's that last point? And that would just be at the top. Okay, so that's kind of the point that I'm interested in, because I'm looking for this min speed. So our first step, remember, draw a free body diagram. So I have mg down, that part's pretty easy. And then there's one more force down as well, and it's coming from that string, right? That string is actually going to pull it down a little bit, and so because it's a string, it's going to be tension. So next, XY chart. Since I only have forces in one direction, I don't need to worry about the XY chart, and I will be doing my Fnet. So Fnet equals, and the question is, this is a circular motion style question, which means that I need to make sure that the forces are positive or negative correctly based on the direction of the acceleration. So remember, if you're going in a circle, your acceleration is always towards the center of the circle at whatever point you're at. So at the top, the center of the circle is down, so both mg and t are both going to be positive. Now, since I'm going in a circle, I use my special Fnet, so instead of ma, I will use mv squared over r equals mg plus t. Now, I'm trying to make v as small as possible, right? I want to make that a small number, which means I need to kind of think about what can I change in order to make v smaller. Well, I can't change v, I can't change r, I can't change m, I can't change g. The only thing I can possibly change is t, and I want to make t as small as possible so that v will be as small as possible. So if I'm pulling on a string, what's the smallest force I can pull with a string? Well, I can't pull negative with a string, so the smallest possible number is 0. So this t is just going to go away to 0. And that will leave me with mv squared over r equals mg. So m's cancel, I'm solving for v, so v equals root gr. But I don't want to use r there, I actually want to use capital L, since that's the length of the string. So that's the sort of an easier, maybe, style question for circular motion. Now let's maybe look at something a little bit trickier. So I'm going to have a car, and this is sort of a top-down view of a car. So this is the top of the car, and it's rounding this turn. It's going to have a turn radius of r. The car will have a mass of m. There's going to be a coefficient of mu, and it says find the coefficient of friction, mu, for, or let me change this. Oh, never mind. So find the mu for a maximum speed of v. Okay, so I want to find this mu for a max speed of v. Now, the first thing you want to ask yourself is, what force actually causes me to go in this circle, to complete this circle, to actually make this curve? And a good way to think about this is, what would happen if the road was just a sheet of ice? Would you be able to turn at all? No, you wouldn't be able to turn. You just kind of go straight, right? You turn the wheel and you just keep going straight. So friction is actually the only force that's going to contribute to my Fnet. Now, I also have Fn, like towards you, and mg straight down, sort of into the screen, right? And then Fn out of the screen in this scenario. Now we can go ahead and plug in. So I have mu Fn equals Fnet. Remember, I'm going in a circle, so special type of Fnet, which would be mv squared over r. Now Fn in this case, right, if I draw the sort of view where the car is coming straight at me, so something like this, right? My radius is here, my friction is here, I have mg down and fn up, that means fn will equal mg. So I'll have mu mg equals mv squared over r. The m's cancel. I'm solving for mu, so I get mu equals v squared gr. Okay, but I would want to change that to a capital R. So that would solve for v. You could also solve for v where it's using find the max speed. Okay, and so this kind of explains why it's important for cars to have grippy tires, right? Especially as you're rounding corners. The faster you can go that corner, you can go faster if the coefficient of friction between the tire and the road is a higher number. Last question we have is we're going to have a satellite, so just kind of drawing a satellite, right? And then we have the Earth, and this is going to be orbiting the Earth, and the distance from here to here we're going to say is just capital R, and we want to know what speed will it orbit at. Okay, so for this one, we are going to go ahead and draw a free body diagram. There's only one force actually acting on this satellite, and that's what? Gravity. But remember, we don't want to use mg because mg is only effective really close to the surface of the Earth, right? So we're actually going to use big G, where big G, F big G is equal to G mm over r squared. Remember, this is the gravitational constant. This is the one of the masses, so here that's the mass of the Earth. This little mass is going to be the mass of the satellite, and then r is the radius, the distance from the center of the satellite to the center of the object it's rotating about. Now we're going to have something like F net equals F big G. Let's go ahead and plug in F net. Since I'm going in a circle, it's going to be mv squared over r equals F big G will be G m over r squared. These little r's will cancel because this is the mass of the satellite, this is the mass of the satellite, and then one of the radiuses will also cancel. So I'm left with v squared equals gm over r, and v equals root gm over r, where I would want capital R since I defined it as capital R. And that's circular motion. So those are 3 good examples to kind of help you solve some of the circular motion questions. So this is sort of an overview of all of forces. Hopefully you're able to kind of understand all these different types of questions that you can potentially have. And I look forward to seeing how well you do on the AP test. Thanks so much.